The cyclic model of the universe proposes that the cosmos undergoes an infinite series of expansions and contractions, creating an eternal cycle of big bangs followed by big crunches. In this framework, rather than originating from a singular event approximately 13.8 billion years ago, the universe continuously evolves through these cycles. Each cycle begins with a big bang, leading to expansion, and eventually culminates in a contraction phase where the universe collapses back into a singularity, only to rebound in another big bang, thus restarting the cycle. This model challenges the traditional Big Bang theory, which presents the universe as having a singular beginning marked by the explosion of space from an incredibly hot and dense state. The Big Bang theory implies a finite history, indicating that the universe has been expanding since that original event, without the possibility of a reversal into a crunch. In contrast, the cyclical model assumes that time is infinite and that the universe has no beginning and no end. Instead, it promotes a stronger, more modern vision of global evolution. One of the driving concepts behind the change model is the interaction between gravity, dark energy, and other forces that dominate the universe. As the universe expands, the effect of dark energy increases, which may lead to an accelerated phase. Finally, the theory says that this acceleration is short-lived, after which the momentum becomes strong enough to begin the deceleration phase. This cycle would repeat indefinitely, presenting a fundamentally different perspective on the nature of cosmic events compared to the static one of the Big Bang theory. Several variations of the cyclic model, including those informed by string theory, have emerged to address various issues raised by the conventional understanding of the universe. This approach seeks to provide insights into the behavior of cosmic structures and the nature of inflation, while simultaneously addressing the fate of the universe. By proposing a model in which the universe is in a perpetual state of rebirth, the cyclic view invites further exploration of fundamental questions regarding time, space, and the cosmic evolution we observe today. The ekpyrotic scenario presents an alternative view of cosmic creation and evolution, positing that our universe originated from the collision of two three-dimensional brains in a higher dimensional space. Rather than emerging singularly in the traditional Big Bang event, this model suggests that the universe emerged from a series of interactions between these brains. The term ekpyrotic is derived from the ancient Greek word for fire and refers to the idea that a collision can produce a very intense event, thus creating the necessary conditions for evolution of our world. In this framework, these two brains are considered to be in a higher place called mass. These brains are not just smooth surfaces, but may contain substance and energy. When two such nuclei collide, a large amount of interaction energy is released, creating an expansion similar to inflation, which forms the basis for the development of the visible universe. The ekpyrotic model best describes how physical phenomena and processes are influenced by brain properties and their interactions. The evolution of the universe in the ekpyrotic state also shows fundamental differences compared to the Big Bang model. But at the same time of creation, the world experiences transformative events involving different minds. These ongoing events create a continuous process of global dynamics. Each collision can lead to a new phase of expansion and contraction, creating the structure of the world in period. This continuous change allows for a more consistent and growing system compared to a world that simply extends from a single source. A significant aspect of the ekpyrotic scenario is its ability to address certain issues encountered in traditional cosmological models, such as the flatness and horizon problems. The interactions between brains could naturally lead to a homogeneous and isotropic universe without invoking an abrupt inflationary period. As researchers explore the implications of this model, They seek to better understand the fundamental principles guiding the universe's creation and evolution, challenging our conventional understanding and exploring the potential interplay between higher dimensions and cosmic phenomena. Brains play a fundamental role in both the cyclic and episodic models, serving as the building blocks of the universe and facilitating the dynamics that explain cosmic evolution in these frameworks. In string theory, brains are multidimensional objects that can exist in higher dimensional spaces, providing a versatile foundation for exploring the structure of the universe beyond traditional three-dimensional perspectives. In both the cyclic and ekpyrotic scenarios, brains are central to the processes that generate cosmic phenomena. In the context of the ekpyrotic model, two brains inhabit a higher dimensional space, often referred to as the bulk. When these two brains collide, the energy released during this interaction initiates a new phase of expansion, setting the conditions for the universe we observe today. This collision is not merely a one-time event. Instead, it can happen repeatedly over time, leading to a cyclical process where each collision creates a new phase of the universe's evolution. This perspective offers a way to visualize cosmic creation that integrates principles from higher dimensional physics and helps explain the characteristics of our universe without invoking a singular initial explosion. Similarly, in evolutionary models, the brain acts as an important component to facilitate the interaction between different regions of the world. This theory begins with the idea that our world is based on a single brain, with other brains interacting with it at a higher level. The collision between these nuclei causes the universe to go through various phases of expansion and contraction, resulting in a series of big bangs and giant explosions. Each match can rebuild the world, can be smoothly transferred from one state to another, creating a dynamic system that is constantly growing. The connection between the brain and the adjacent parts opens up interesting possibilities for the fate and development of the world. By providing a mechanism for interactions that generate energetic conditions necessary for cosmic evolution, these higher dimensional objects challenge conventional views of a singular beginning and present an ongoing process in which the universe can transform continuously. As theories evolve, the exploration of brains enriches our understanding of the fundamental forces shaping the cosmos, inviting consideration of how higher dimensional physics interfaces with our three-dimensional experience. The cyclic and ekpyrotic models provide intriguing insights into what may have existed before our universe and what lies beyond its current state. These frameworks reject the notion of a singular beginning in favor of an ongoing cosmic process, suggesting that the universe is part of a larger, more complex reality. In the cyclic model, the universe is depicted as undergoing endless sequences of expansion and contraction. This shows that there is no specific time for the beginning of the world. Rather, it is part of an endless series of changes. Each cycle has a section dealing with different laws and physical conditions. So, before our current universe, there may have been a universe in the past that went into a singularity and then came back in another Big Bang event. The cyclic nature of this pattern challenges the notion of time and existence and suggests that the universe has always existed on this endless tape. The ekpyrotic model takes a different view by suggesting that our universe arose from the collision of two brains in a higher place. In this sense, the existence of brains suggests that there are forms and structures beyond our three-dimensional world. The space occupied by these brains is filled with many more brains and other higher dimensional objects, creating a vast table of possible interactions. It is this higher dimensional environment that allows humans or structures to exist before our world and create our world through the power of brain collisions. In both frames, the question of what lies beyond our universe is viewed through the lens of higher dimensions and rotational interactions. There may be many other worlds with minds like ours, each with a unique set of laws and physical histories. Rather than a well-defined label or boundary to our world, these models represent a larger world in which different regions can operate under different principles, offering the potential for many aspects of life. These ideas reveal important information about the nature of the universe, time, and the fundamental framework that governs the universe. Cyclic and ekpyrotic models express the need to understand reality beyond the limitations of the origin story. It opens the way to explore the deepest mysteries about the evolution of the universe and its meaning for the past and the future. Support for the cyclical and ekpyrotic models of the world comes from circumstantial observational evidence rather than concrete evidence. Scientists have focused on the phenomena of the world, looking for patterns and phenomena that match the predictions of these patterns. One of the most important is the microwave background radiation, which holds important information about the early universe. In the ekpyrotic state, collision branes can have a distinct signal in the microwave background. These effects are caused by temperature variations or variations in the microwave background that are different from what previous inflation models suggest. Some researchers have analyzed the statistical distribution of these differences to identify signatures consistent with collision events, although clear evidence remains a matter of research and debate. The circular model also aims to address some of the challenges associated with the inflation model. For example, some predictions about the equilibrium and isotropy of the universe can be verified by the large distribution of galaxies and universe structures. Galaxy cluster models may reflect the effects of changes in expansion and contraction. Some observations or distributions were found to indicate that our world is changing, although the connection to cycling is still difficult. In addition, tidal waves produced during the early universe's expansion can provide important data to support these models. If the ekpyrotic or cyclic conditions are correct, they can predict the existence of some kind of shock waves caused by collisions or brane interactions. Although wave-wave astronomy is still in its infancy, the discovery of these signals could add significant weight to the circumstellar and ekpyrotic frameworks. Currently, both models are being tested through real-world observations and background radiation conditions. Even if hard evidence is not found, the search for patterns, oscillations, and tidal waves provide an exciting opportunity to gather data to support or challenge these different models of global evolution. As observational technologies improve and theories evolve, the understanding of these complex models may broaden, revealing deeper insights into the nature of the universe. Quantum cosmology is a field that seeks to apply the principles of quantum mechanics to the entire universe, aiming to understand its origins and fundamental nature through a quantum lens. Traditional cosmology often relies on classical physics and general relativity to describe the universe's structure and evolution. But quantum cosmology introduces the idea that the universe itself may have quantum properties that are essential for understanding its beginnings and dynamics. One of the main goals of quantum cosmology is to address the question of what came before the Big Bang. Traditional models struggle with the concept of singularities, points where densities become infinite, such as the initial state of the universe. The goal of quantum cosmology is to determine these particularities by considering the wave function of the universe, which is a mathematical description of its fundamental nature over time. This wave function contains all the configurations of the universe and provides a possible path to the planet. A popular approach to quantum cosmology is the proposal by physicist Stephen Hawking and his colleagues for a non-local state. This theory shows that the geometry of the universe is small, but has no boundaries, like the surface of the universe. According to this view, as the universe transitions from a quantum state to a classical state, it will evolve the unique properties associated with the Big Bang, allowing for a better understanding of its origin. Additionally, Quantum cosmology explores the idea of multiple histories or paths through which the universe could evolve. Inspired by the principles of quantum mechanics, where particles can exist in superpositions of different states, quantum cosmology posits that the universe could follow various trajectories. These trajectories can lead to different physical scenarios, suggesting a richness and complexity to the universe's development that goes beyond deterministic models. By merging concepts from quantum mechanics with cosmology, this field attempts to deepen our understanding of the universe's origins, structure, and underlying laws. Quantum cosmology not only aims to provide answers to fundamental questions about existence, but also bridges the gap between the microscopic world governed by quantum phenomena and the vast cosmic scale of the universe. As scientists continue to refine their methods and accumulate empirical evidence, quantum physics could revolutionize our understanding of reality. The Wheeler-DeWitt equation is a fundamental element of quantum physics, a key equation to describe the nature of the universe. Developed by physicists John Archibald Wheeler and Bryce DeWitt in the 1960s, this equation emerged from attempts to integrate quantum mechanics with general relativity, especially in the context of the whole universe rather than individual particles. The purpose of this equation is to explain the dynamics of the world at its most basic level and to describe the nature of space and time in a larger framework. An important feature of the Wheeler-DeWitt equation is that it works in space where the conventions of time and space break down. This equation describes the wave function for the universe, representing all configurations of the universe's geometry and chemistry. This wave operation is important to understand the nature of the different phenomena, which are related to the concept of many worlds. In quantum mechanics, particles can exist in a set of states, suggesting that the same principles apply to the universe. The connection to the multiverse comes from the interpretation of the wave function produced by the Wheeler-DeWitt equation. Each solution to the equation can represent a different universe within a larger multiverse context. When considering various configurations of space, time, and matter, the wave function can populate a vast landscape of possibilities. This means that the act of observation or measurement in this framework could lead to collapses of the wave function that result in distinct outcomes, effectively creating branches in which different universes exist simultaneously. This idea dovetails with the concept of the many worlds interpretation of quantum mechanics, where every potential outcome of a quantum event occurs in a separate branching universe. In this sense, the Wheeler-DeWitt equation may suggest a multiverse, a collection of coexisting parallel universes arising from different solutions and arrangements. Each universe's state can be thought of as part of a vast cosmic tapestry, woven from the fundamental dynamics and interactions encapsulated within the equation. By providing a mathematical basis for understanding the universe in a quantum context, the Wheeler-DeWitt equation plays an important role in the debate about the origin and probability of the universe. And the underlying principles that govern the universe. The wave function of the universe is a concept in quantum physics that describes the nature of the universe. It describes all the geometrical, chemical, and energetic configurations of the universe over time. This wave function comes from the application of quantum mechanics to the universe, specifically the Wheeler-DeWitt equation, which works in the same way as the quantum mechanics description of particles and systems. This wave function contains all possible states that the world can exist in, and acts as a probability distribution of outcomes rather than a single decision path. Since the wave function of the world contains all possible histories and structures, it allows for many phenomena to become one. When a measurement or observation occurs, the wave function collapses and results in a result that corresponds to the observed reality, but other things appear in parallel or branching forms. The implications of this wave action extend to the idea of multiple universes. Each wave function solution may correspond to a different world with different physical laws, equations, and first conditions. In this way, worlds different from ours coexist and may respond to a single-dimensional framework. These different conditions may be of a specific nature, shape, or form, depending on the probability of the wave operation and the type of configuration involved. Investigating the wave function of the universe raises profound questions about the existence and nature of reality. If multiple worlds emerge from the different effects of wave action, it opens up ways to explore what these realities look like and how they interact or exist separately. This framework encourages a broader understanding of the world, showing that our world is seen as just one part of the cosmic structure. The concept of the wave function of the universe challenges our traditional notions of space, time, and reality, inviting contemplation about the vastness of potential existence beyond what we can observe. As researchers continue to grapple with the implications of this concept, the pursuit of understanding the universe's quantum foundations reveals a rich tapestry of possibilities just waiting to be explored. Quantum cosmology presents a novel approach to the problem of time in the early universe, a challenge that arises primarily from the limitations of traditional physics when applied to cosmic conditions. In classical general relativity, time is treated as a continuous linear progression that flows uniformly. Yet this perspective becomes complicated near singularities, such as the one proposed at the beginning of the universe during the Big Bang. At these extremes, conventional notions of time break down, leading to the question of what time even means in that context. One of the main ways quantum cosmology has approached the question of time is the theory of the wave function of the universe, specifically as described in the Wheeler-DeWitt equation. This equation does not include time as an independent variable like classical theories. Instead, he considers the shape of the world as a function of its geometry and material configuration. This method suggests that time may not have been a fundamental property of the early universe, but may have arisen from quantum processes. In this view, time is not a real background against which events occur, but rather a relational phenomenon that results from the interactions and connections between dimensions. In addition, Stephen Hawking's proposal for infinity provides important insights into the nature of time at the beginning of the universe. This model shows that the world has no boundaries in the traditional sense, allowing time to be smooth and finite while avoiding specific situations. Instead of a clear space that marks the beginning of time, the early universe can be said to be a bubble in size, combining traditional concepts of time and space. This approach provides a framework that can be used to determine the time from the decay of wave activity into specific and future states as the universe evolves. In addition, quantum cosmology opens up many histories and paths, where different places can emerge from different situations. Each of these timelines could represent a distinct way the universe might develop, challenging our linear understanding of time. In this interpretation, time is contingent upon the evolution of the universe's wave function and its associated dynamics, highlighting a more complex relationship between events rather than a simple progression. Through these frameworks, quantum cosmology approaches the enigmatic problem of time, suggesting that it may not be a fundamental aspect of the universe, but rather a secondary property emerging from deeper quantum realities. This perspective not only advances our understanding of the early universe, but invites further philosophical inquiry into the essence of time itself and its role in the fabric of reality. Testing quantum cosmology theories lends itself to a fascinating blend of empirical observations and intricate experiments that probe the very fabric of our universe. One of the most important areas of study is the microwave background radiation. These remnants of the Big Bang contain important information about the nature of the early universe. Differences in temperature variation can shed light on size effects that occurred during the world's birth, possibly confirming theories of size stress. Another good method is the detection of horizontal waves. These ripples in space-time, first seen in 2015, are caused by some of the world's most dynamic events, such as black hole mergers and neutron-star collisions. Analyzing these waves helps scientists understand the quantum properties of gravity, especially during extreme conditions where traditional physics might break down. The detection and measurement of gravitational waves can provide clues on how quantum mechanics operates on a cosmological scale. Moreover, experiments attempting to observe primordial quantum fluctuations offer yet another layer of validation for quantum cosmology models. These fluctuations are thought to be responsible for the large-scale structure of the universe we see today. If researchers can detect these fluctuations, perhaps through the sensitive instruments that measure the distribution of galaxies or the density variations in the cosmic microwave background, it would bolster the argument that quantum principles influence the universe's earliest moments. Finally, future technological advances, such as those in quantum computing and high-energy particle physics experiments, may also contribute essential insights. These tools could help simulate early universe conditions, explore fundamental particles, and reveal the connections between quantum mechanics and gravitational forces. As our observational technologies improve, the boundaries of quantum cosmology will continue to expand, inviting scientists to uncover deeper truths about the universe's birth and evolution. Black holes have long captured the imagination of scientists and the public alike, serving as mesmerizing enigmas in our understanding of the cosmos. One of the most captivating theories suggests that black holes might serve as gateways to other universes or regions beyond our own. This theory includes the idea of worms, horizontal holes in space-time that can connect distant parts of the world, even all different worlds. Imagine a shortcut through space, where a journey of millions of light-years can be reduced to a fraction of the time by navigating through a wormhole created by a collapsing star. In theoretical physics, some models say that when matter falls into a black hole, it can form a bridge to another point in space. The Einstein-Rosen bridge is widely known, based on the equations of general relativity. Although the mathematical framework describes the nature of these relationships, the functional aspects remain unclear. The chaotic environments and extreme gravitational forces near black holes could present insurmountable challenges, making it unclear if anything could survive a journey through such regions. Moreover, the notion of a black hole leading to a different universe raises questions about the nature of reality itself. The multiverse theory, which posits the existence of multiple, perhaps infinite universes, complements this idea. Should black holes act as portals, they might connect our universe with others that contain different physical properties, constants, or dimensions, leading to a wealth of possibilities beyond what we can currently imagine. However, the current understanding of black holes suggests that any information or matter crossing the event horizon is likely lost to the outside universe, leading to the so-called black hole information paradox. Scientists are exploring concepts such as the principles of holography and quantum entanglement to incorporate these ideas. As research and theoretical models continue to develop, black holes will become a platform for understanding the complexity of our universe and the possibility that they could connect us to the places beyond us. The discussion of black holes is a deep problem in theoretical physics that arises from the connection between quantum mechanics and general relativity. The point of this paradox is to ask what information falls into a black hole. According to quantum mechanics, information cannot be destroyed. This principle asserts that the nature of a quantitative system can be determined from its results. But when matter crosses the border of a black hole, it becomes irreversible. As a black hole evaporates over time due to Hawking radiation, the question is Is the information about what fell into it lost forever, or did it escape? This hypothesis has caused great debate among physicists, based on various concepts and theories that seek to reconcile these different perspectives. The main difference is that the information is not lost, but instead encoded in the event horizon, a concept that gave rise to the concept of holography. This principle states that all data in a volume of space can be represented as a binary information structure at the boundary of that region, thus preserving the information even if it appears to be lost. Because black holes are beyond understanding black holes, if information is never lost, there may be a reality beyond our visible world. Some theories suggest that the solution to the paradox may involve several factors. In these models, information lost in one world appears in another, involving communication between different locations. Thus, when we contemplate the fate of information within a black hole, we might also be considering pathways to alternate realities or distinct universes where different physical laws apply. As researchers strive to untangle these intricate connections, the study of the black hole information paradox continues to fuel excitement in cosmology. Conversations around this topic not only challenge our understanding of black holes and the fundamental laws of physics, but also tantalize our imaginations regarding the nature of the multiverse and the possibilities it presents. The resolution of this paradox could very well redefine our concepts of reality, existence, and the interconnectedness of all things within the cosmos. Hawking radiation is a groundbreaking concept proposed by physicist Stephen Hawking in the mid-1970s, positing that black holes are not entirely black, but emit radiation due to quantum effects near the event horizon. This phenomenon results from interactions between particle-antiparticle pairs that spontaneously appear and disappear in the vacuum of space. When that pair forms near a black hole, one particle falls into the black hole and the other escapes, eventually losing mass over time. Therefore, this radiation is said to cause black holes to shrink and possibly die. The implications of Hawking radiation are profound and challenge the traditional view of black holes as static, unchanging entities. If black holes can produce energy and eventually disappear, it raises important questions about what happens to the information stored inside. This relates to the proverbial black hole paradox. If a black hole shrinks and loses information, it violates the basic principles of quantum mechanics. Therefore, an understanding of Hawking radiation is essential to establish a unified framework that combines quantum mechanics and general relativity. In addition, Hawking radiation is fueling theories about the nature of the universe and its structure. If black holes can emit radiation and lose mass, can this process also create new universes? Some theories propose that the energy emitted as Hawking radiation could seed the formation of new cosmic structures, or even isolated regions of space-time that embody different physical laws, thereby hinting at the existence of a multiverse. In this view, black holes might act as both destroyers and creators, facilitating connections between diverse realms of reality. As scientists continue to explore the implications of Hawking radiation, the pursuit of a unified understanding of quantum physics and gravity remains a tantalizing challenge. Each insight gained from studying black holes will not only refine our comprehension of these mysterious objects, but also illuminate the potential pathways connecting our universe to others, shaping how we perceive the cosmos and our place within it. The fuzzball theory presents a fascinating alternative perspective on black holes, diverging from traditional views by proposing that black holes are not infinitely dense points of singularity, but rather complex, stringy structures. The wing phase framework, derived from string theory, suggests that fundamental particles are single-shaped strings, rather than points, which describe black holes as a bundle of these strings. According to this example, what we call a black hole is a collection of filaments in a highly excited state that are spread out over a large area rather than staying in one place. One of the most interesting aspects of the fuzzball theory is its possible separation from the informational paradox of the black hole. Unlike ordinary black holes, which seem to swallow information irretrievably, slow balls encode this information into their string architecture. Therefore, information about what is happening in the phase ball is not lost. However, it has been preserved in the structure and dynamics of football itself. This work is consistent with the principles of quantum mechanics and provides a better connection between energy and quantum theory. The implications of the spherical theory extend far beyond the phenomena of black holes and the universe of other planets. If it is possible to understand that black holes are slow spirals, it will open up interesting possibilities for connecting them to other regions of space, even to different worlds. The spindly shape of the fuzzy balls can provide a path or portal through which various aspects of space can emerge, hinting at the existence of a multiverse where black holes serve as gateways to alternate realities with distinct physical laws or features. By expanding our understanding of black holes through the fuzzball framework, researchers may uncover new dimensions of cosmic architecture. The interplay between strings, gravity, and the information encoded in black holes holds the potential to address fundamental questions about the universe, while shedding light on the tantalizing prospect of multiple universes coexisting alongside our own. As the exploration of fuzzballs continues, it invites not only a re-evaluation of black hole physics, but also a broader contemplation of the structure of reality itself. Primordial black holes, which are thought to have formed in the first moments after the Big Bang, offer a unique window into the conditions of the early universe. Unlike stellar black holes, which originate from the collapse of massive stars, primordial black holes are thought to have formed directly from density differences in hot and dense matter of the world shortly after creation. By studying these mysteries, you can understand the nature of the universe's infancy and may shed light on its formation and evolution while challenging observations. An important characteristic of the first black holes is their potential mass range. They can range from very small, with a mass less than an asteroid, to larger masses, similar to stellar black holes. In particular, the existence of supermassive black holes raises interesting questions about dark matter. Some theories propose that if such black holes exist in sufficient quantity, they could contribute to the elusive dark matter that makes up a substantial portion of the universe's mass. Investigating their properties could therefore also enhance our understanding of the dark universe and its components. Furthermore, primordial black holes may offer clues about other realities or different regions of the universe. If certain mass ranges were associated with multiple formation processes or different physical conditions, the formation and characteristics of primordial black holes could hint at the multiverse concept, where our universe is just one of many, with distinct physical principles. Researchers are exploring how primordial black holes might connect to different cosmic structures, perhaps acting as gateways to alternate regions of space-time with unique properties. The study of ancient black holes is linked to the discovery of cosmic inflation, suggesting that the universe expanded rapidly shortly after the Big Bang. Understanding how density variation affects the formation of these black holes can help explain our general theories about the accretion and formation of supermassive structures. As scientists continue to investigate the mysterious nature of ancient black holes, they will not only enrich our knowledge of the past, but also increase the debate about the existence of real objects. Many and push the boundaries of our understanding of the world.